In this video, we're going to do a vector surface integral over the same region or the same solid that we've been looking at. And this time, the difference will be that we'll be looking at a vector integral. So we're looking at the surface, and because I'm looking at a vector integral, I do need to specify which direction or how I'm orienting my surface. I'm going to be orienting it with outward-facing normal vectors. So basically that means that my normal vectors will look like this, or maybe like this if we're on top. Something like that. And the formula for the vector surface integral of a vector field f ds, there's actually two formulas that we might be interested in. One of those formulas, well, there's actually, a handful, but one of those is going to be, we're going to look at the integral over d of f composed with our parameterization dotted with our normal vectors, and this assumes that our normal vectors are pointing in the proper direction. If they're not pointing in the proper direction, then we will need to do a little bit of modification at the end, basically just make our answer negative. So we can use that formula, or we can even turn it into a scalar surface integral by instead dotting the vector field with a unit normal vector pointing in the appropriate direction. And sometimes it's easier to find that unit normal, and sometimes it simplifies our function, like it will here. And we don't even really need to worry about the nuts and bolts of parameterizing something. So we're actually going to get to use both of these formulas in this video. There are, of course, a couple different ways you can represent n. If you have a parameterization, which we'll use in this video, it's going to be given by Ts cross Tt. If you're given a function instead, then n is going to be given by negative gx, negative gy, positive 1. So we're going to use a parameterization. If you remember our x, this was s of s comma t. Pretend there's an s there. If you remember our parameterization was something like s cosine of t, s sine of t, s. And if you take a look, when we calculated n ended up being negative s cosine of t, negative s sine of t, 1. And if you notice, those vectors actually point kind of like this. They're pointing inside our surface. And let's also take a note. We are only talking about the sides right now. We are going to once again break this up into the sides and the top. So this is all for the sides. So we're going to need to make our answer negative because this points the wrong way. Okay. So let's go ahead and set up our integral. So we're going to be integrating this d, remember from the previous video, is just kind of when we're using the parameterization, this represents the bounds in our parameterization. So s is going from 0 to h, and t is going from 0 to 2 pi. What's xz? Well, my x is s cosine of t. And my z is s. Yz, that's going to be s sine of t. Times s. And then my last component's just 4. And I'm going to dot that with n. And we see that n is negative s cosine of t, negative s sine of t, and 1. We'll be integrating all that ds dt. That's a mouthful. But this is actually going to simplify down quite nicely into, well, that's going to be s squared cosine. So I'll have s squared actually cubed. So s when I take the dot product. So it's negative s cubed cosine squared of t plus negative s squared, cubed, sine squared of t. And then we'll have plus 4 ds dt, which you might notice just equals the integral from 0 to 2 pi, 0 to h of negative s cubed plus 4 ds dt. So that's nice. When I integrate that, it's not going to be too bad to integrate. When I integrate in respect to s, I'll get negative s to the 4th over 4 plus 4s ds dt. When I evaluate it from not ds dt, that's going to be evaluated from 0 to h. So that's going to be the integral from 0 to 2 pi, negative h to the 4th over 4 plus 4h dt. That's all a constant in respect to t, so I can just multiply that by 2 pi to get my final answer. So I'll have 2 pi negative h to the 4 over 4 plus 4h. But remember, this pointed in the wrong direction. So we actually need the negative. So this is actually going to be, we can write 2 pi 4h minus h to the 4 over 4 instead. And that'll do the job. So we have our sides. This is the integral for the sides. Now I want to do the integral of the top. And we actually have a nice trick that we can use here. Let's go ahead and look at this version. So instead of finding, I could find a new parameterization. For the top. But I notice the normals, the unit normals pointing in the right direction, are given by, well, it's always just pointing straight up. So instead of going through all this parameterization, I'm just going to look at the surface integral over S of f dot n ds. And again, we're integrating over the top, which is a circle with radius h. So what's this going to be? Well, this will be xz, yz, 4, dotted with 0, 0, 1. And again, we're going to be integrating this. I should call this like ds2 or something because we're talking about the top here. This was like maybe the ds1 or s1 of f ds. Okay. Which just means that we have the integral over s2 of, that just ends up being 4 ds. And since this is an integral over a circle of radius 4, you could think about this as 4 times just this, and this is surface area. So this is just going to equal 4 times the area of a circle with radius h, which is pi h squared. And that's it. So, to conclude, the final answer, when I put those two parts together, is going to end up being the integral over the sides, which is 2 pi 4h minus h to the 4 over 4, plus the integral over the top, which was 4 pi h squared. There you go. So we saw kind of two different techniques to do this problem. One technique used the parameterization, and we, got a decent integral when we did that. And the second technique used direct knowledge about the unit normals, and that worked out especially nicely because when I dotted the unit normal that I had with my function, I got a constant, which meant that it was really easy to integrate over the surface. It was just that constant times the surface area. So there are a couple of examples of doing vector surface integrals.